This is first video related to lecture 9. So it's part 1 of lecture 9. And lecture 9 is devoted to broadband modem technologies. Just to remind you, these broadband modem technologies are a part of part 3 of lecture series, and this part 3 was related to general modem design technologies. And as I have emphasized many times, we are not going to the detail of implementation of the modems. We are just talking about intuitive understanding of modems and how their performance compare with one another. And what we did in there, we divide this part of the lectures in 4 lectures. The first lecture in that 4 lecture series was basic narrowband modem technologies. In there, I just reviewed all the modem design technologies which are used for wireless LANs and cellular networks. And basically, I was just talking about how these things work and what is the performance in additive noise channel. Means that you design the modem and you put it back to back. Then in the second lecture in that series, which was lecture 8, we started to talk about fading, effect of fading, and then we said that, okay, harmful effects of fading is compensated by diversity techniques. And then as an example, I gave you coding, one technique that was taking advantage of a sort of time diversity, if you want to call it. And also we talked about space-time coding and MIMO systems as techniques which are useful in counteracting the effect of fading. Throughout that discussion, I was holding that I have narrowband communication. And narrowband communication basically means that when I send a pulse, I receive the same pulse form. Okay? Means that because of the multipath, my signal does not spread to the next symbol, my pulse. I will show you some picture on that in a review. Now, starting this lecture and next lecture, we talk about wideband communication techniques or wideband modems. Wideband modems are the ones which are operating at a time that your data rate is comparable with inverse of RMS multipath spread of the channel. Narrowband is the time that your data rate is less than like 10% of inverse of RMS Doppler spread of the channel, if you want to say. But in action, the difference is that if I send a pulse in narrowband, I receive the same pulse shape. In wideband, the shape of the pulse gets distorted due to multipath. That's the basic difference. And then the question is that how you can remedy that situation. And then I review the techniques which are applied to remedy this situation. Okay. Now, there are 2 types of technologies. One are the so-called like traditional, if you want to call, that I cover in lectures 9, which means that basically I have the same modems that I had before. I don't change the transmitted symbol, but in the receiver I try to do some stuff. Or I change the transmitter, but still the pulse shape is not that much changed. The second technique is like a spread spectrum technique, in which I'm either changing the carrier frequency or I'm changing the transmitted symbol. And we treat that in lecture number 10. The importance of techniques which are used like equalization, a smart antenna, OFDM, most of them are used in wireless LANs, local area networks, when I want to have very bandwidth efficient, high data rate in one single channel. Spread spectrum techniques, in particular CDMA technology, was the choice of third generation cellular networks. So from that point of view, they are very important. So we consider these two in two separate things, Lecture 9 and Lecture 10. Now, just to remind you, because everything that I would like to do in my lecture series in here is to provide you an intuition about why different transmission technique has been applied to certain wireless networks. So to have that intuition, it's good to review what we had before to continue in this lecture. If you remember in my previous lecture, Lecture 8, I talked about fading. I said, well, this is what will happen. The received signal goes up and down, and this goes up and down causes these fadings. This is the signal-to-noise ratio which goes up. And this fading is caused because in narrowband communication, I have different paths, and these different paths, they have different phases, and they may come against one another and cancel each other. When they cancel each other, I will have a deep null. I will have a fade. They may add together. If they add together, I have very strong and healthy signal. So my problem in radio channel, in multipath radio, is that once in a while, the paths are coming against one another and they cause fading. What will happen when we go to the fading? My error rate goes way up. What is the highest error rate that you can have? Is 0.5. Because you are sending a symbol and it's just like flipping a coin. Okay? What is the lowest probability of error? Is 0, but we never get to 0. We have like 10 to the minus 5, 10 to the minus 10, that's 10 to the minus 8, 10 to the minus 2. Depends on the system. If I have a voice application, 10 to the minus 2 is fine. 1 bit error in 100 bit error. If I have data, even uncoded data, I want 10 to the minus 1. For coded, people want no error, absolutely no error. So they try to retransmit the things if they feel that there might have been an error there. And that makes sense because in data, I'm sending numbers. I'm sending text. Even if I send a book from one place to another place and one word is changed, people don't like it. And if I'm in the banking, one number is very, very bad to be changed. So as a result, we have different requirements for voice and data. But anyways, the raw data that I have, I can never eliminate the error rate. If I want more secure communication, I will have like error correction codes and retransmissions. This is what they do for radio, for wherever you are. Okay, but we are talking about only raw data. And for raw data, in these areas, I have error rates like 10 to the minus 2, 10 to the minus 5. But when I have fade, I have error rate of 10 to the minus 2. And we observed that last time, because of this phenomenon, happens like 10% of the time, my error rate goes way, way high. And the only way to avoid the error rate is take this average signal-to-noise ratio and boost it up like 30 dB, 1,000 times. That's the only way to avoid the fade. Okay, and that's a lot of things. Then the second thing that we did in the last lecture, we said, okay, the easy way to remedy the effect of fading is that find two sources which are independent fading. Two sources of received signal which are fading independent from one another, and we call them diversity branches. The easiest form of creating diversity branches is to create two antennas and put them a little bit away from one another so that the received paths in those places, they have different phases. How can I change the phase? How fast phase changes? You remember that phase changes omega tau, and that tau is related to lambda. So if I go like around lambda away and I put two antennas, they are like 2 pi difference in the phase. Okay, so I have plenty of now room for these paths to combine with. So I can put, if I have independent, like Rayleigh fading channels, I can put even lambda over 4 apart, the antennas. And then the phases changes. Then when phases changes, if in one location I have fade in here, I will have fade in the other one at a later time. So I have 2 sources of independent fading. And then I look at both of them, and whenever one of them is in fade, I use the other one, for example. That was the summary of what we had in here. So if you want to just put it in your mind, as a radio engineer, if you want to design a modem, you have to provide diversity. So up to in the last lecture, I showed you how effective is diversity. For example, I showed you curves like this. If I have no diversity, my performance goes like this, and this is my performance without fading. And I showed you that the difference between this one and this one at error rate of 10 to the minus 5, for example, was something like 35 dB, if you remember. That's what I showed you last time. But if I now create, like, this is 10 to the minus 5, and this one and this one. This we had it last time. But if I go from fading channel to 2 order of diversity, I save like 20 dB. And then if I put like 4 antennas, I will save another like 10 dB, close to 10 dB. If I have 8 antennas, my performance gets very close to non-fading. Okay, so my objective, I mean, what I showed you last time, this is the summary. Fading is cause of problem in radio channels. Go and find methods to create diversity, because diversity is the remedy to coding. How effective is diversity? If diversity is independent, this is how effective they are. But just to start with, I told you 2 types of game that you can play to provide diversity. One was you can add coding. The other one is you can add multiple antennas. And now, if you add multiple antennas, we had this physical problem, especially in the receiver, which is always a small gadget. How can you put many antennas? So I have to put it at transmitter. If I put it at transmitter, then I had this problem of I cannot create like maximum ratio combiner, which is the optimum combiner. Then we talked about space-time coding, in which the bits that I'm transmitting in the antennas, in the base station, I shuffle them somehow, and I code them. So I send one bit in this antenna, the other bit in the other antenna. Then next time I repeat the past one in the first one. So anyways, so somehow when I'm out of fade, I have some bits. So that's the so-called space-time coding, concept behind space-time coding. Do you remember that? I'm shuffling the 2 bits between the 2 antennas. So one of them goes to fading, I lose it. But since I'm repeating it in the other antenna, I will pick it up in the other antenna. And we showed that basically a space-time coding with like 2 transmit antenna, 1 received antenna, very simple one, the Alamuti code, can do performance very close to this thing with 2 transmit antenna and 1 received antenna. Okay, so that was the summary of the last one. I told you just to remind you that this is what we are after. Okay, we are after providing diversity. Okay. And these diversities, remember, they are uncorrelated. If they are correlated, they will change. So if you want to summarize in the last lecture, I talked about this diversity combining techniques also. I talked about selective combining, means that between 2 received diversified signal, I select the one which is the stronger. Then we had equal gain combining, the received signal, they add as they come. Maximal ratio combining, received signal is weighted by its magnitude, and then they are combined. And then I told you that this maximal ratio combiner is a sort of like match filtering in diversity. This is the optimal receiver in diversity condition. So I always strive for this thing. I strive for maximal ratio combining because it provides the best performance. In order to do that, I need to estimate the channel multiplied with the received signal. Estimation of the channel is not that difficult. I just pass it through a low-pass filter if it is just single tap. Then that's more or less whatever that we had in lecture 8. Now in lecture 9, I want to start to talk about broadband modems. And I talk about 3 topics. First is frequency selective fading and a channel model which represents frequency selective fading. Then I talk about discrete match filter and equalization technique which provide time diversity for time diversity is provided by discrete match filter and equalization. And I use this discrete channel model that I have developed in here to explain equalization and discrete match filtering. And then the third part of the lecture, I talk about smart antennas a little bit, how they work, and I talk about OFDM modulation. So basically, I'm talking about equalization, OFDM, and smart antennas, if you want to call. These are the 3 techniques that people evaluate whenever they want to have broadband modems. Who wants to have broadband modems? What is the meaning of broadband modem? Broadband modem means high data rate modem. If I have a voice application, I have an encoder which is like 10 kilobit per second. The data rate is fixed. What I need to do is that I need to increase the capacity. Means that I have to change my medium access control. But when I have single line modem for data application, like wireless LAN or for mobile data applications, when I have single channel like that, my medium access control is like carrier sense multiple access or whatever, is a random access or whatever, could be TDMA. But for one instant of time, I want to have very high data rates. So when I say that like 802.11b is 11 megabit per second, is only the data rate on the channel. And I want to increase it from 11 to 54, so I go to 802.11a or I go to 802.11g. Okay? So I want to increase the data rate. And only for data applications, which are bursty. Okay? There are 3 techniques, basically, that people have. Who is interested in that? More than anybody, 802.11 was interested in that. And more recently, people who want to provide 3rd generation and beyond means that internet access, wireless internet access type of provider. Okay? What they had was that they designed the 2nd generation cellular and 1st generation cellular for voice application just to increase the capacity. And then they end up to like GSM or IS-95. And for those type of like applications, data rates cannot go more than like 9600 or things in that run, like modems. So they start to change these formats to go to higher data rates. And in order to go to higher data rates, they have to look into different technologies. But they are restricted to the bandwidths. In wireless LANs, they are not restricted. They are developing new technology only for data. For mobile data, they had these technologies for the voice. They had to modify it. For wireless LAN, this is for data that I am designing everything. So 3 techniques have been considered, actually, by standards, HyperLAN 1, HyperLAN 2, and then 802.11. One is using equalization. One is using smart antennas. One is using OFDM. These are 3 technologies that they were examined for wireless LANs. And then the 1st generation of 802.11 was anyway a spread spectrum communication that we will study in the next lecture. But these 3, like using the antennas, first time was used by Alter. Alter was one of the early wireless LAN products working at 18 to 19 gigahertz. license bands designed by Motorola. And then equalization was evaluated by Hyperland 1 standard. And then OFDM was the one that was selected by 802.11a, 802.11g, and Hyperland 2. Now, what we do, we have one additional one, which is discrete match filter. Discrete match filter actually can be, first time of the, I think, implementation was done for tropo modems, troposcatter modems. And was a design that was done actually in Raytheon, here in Massachusetts, and was in mid-70s. Equalization for the first one was done with another company, which is Signatron, again in the mid and early 70s, again in Massachusetts. That was in Bedford, Massachusetts. And then OFDM was a thing that was studied more recently for this type of field. Discrete match filter, equalization, a smart antenna, OFDM, 4 technologies that I will look at. And I want to give you some intuitive understanding of this thing and how they emerged, and how they provide diversity, really. Basically, all of these techniques, they provide diversity. The type of diversity that they produce sometimes is referred to as implicit diversity. Means diversity which exists inside, or in-band diversity, inside the signal, as opposed to explicit, like antenna diversity, okay? Or diversity which comes from coding. But anyways, let me just start this lecture first with frequency selective fading and introduce you an overall channel model in frequency selective fading. Basically, if you remember, I had this figure last time. Perhaps I sketched it by hand. I had this comparison between narrowband and wideband. If I have a channel like this, if I have narrowband communication, means that my pulses are very wide with respect to spread of the channel. Okay, this is narrowband communication. Narrowband communication means that, inverse of this thing, inverse of this distance, which happens to be my data rate. If this is t, my data rate is r equals to 1 over t. This thing is much smaller than RMS multipath spread. In here, I have a tau RMS. And 1 over t is much bigger than tau RMS, bigger than 0.1 over tau RMS. This is what I had last time. Okay? I mean, picture-wise, what will happen is that in cases like that, I send the pulse, first path comes in here, second path comes in here, third path comes in here. They are almost on top of one another. All the paths are coming on top of one another. But these paths, these signals, they have different phase. And they add together, and I have a pulse shape which is the same as what it was transmitted, but the amplitude of this pulse shape is going to change, go up and down, depending on the phase of the received paths. Okay? This is narrowband communication. So the only thing that I have is the so-called flat fading. And my pulse shape is the same, just the amplitude changes up and down. Okay? That was narrowband communication. We discussed this last time, and we said that if you provide diversity, if you want to create diversity for that, you put 2 antennas away from one another. Or add some coding to that. Or combine the 2. Okay? Now, what about wideband communication? Wideband means what? Wideband or broadband means what? Increase your data rate. Huh? If you increase your data rate, what will happen? This T that I had becomes narrower. Huh? And then my R, which is 1 over T, becomes comparable to 1 over tau RMS, for example. So as I increase my data rate, the width of my pulse becomes comparable with the spread of the multipath. Okay? Then what will happen? What will happen is that I send this pulse, I receive first pulse in here, second pulse in here, third pulse in here. And if I add this first pulse, second pulse, third pulse, I get something like this dotted line. I get something like this. This waveform is no more like transmitted waveform. So what? So what is that? Now the length of this pulse is T something roughly plus tau M. Tau M is this spread of here. Maximum tau spread. You follow me? Okay. So what? So what is that? In the transmitter, every T seconds I'm sending a pulse. At receiver, I receive pulses which are now overlapping, and they cause this intersymbol interference. Okay? So if I have a multipath fading, and I increase my data rate above fractions of 1 over tau RMS, my waveform now changes. And I'm facing a new problem. And if I'm not doing anything about it, I have this intersymbol interference. Means that pulses, they interfere with one another. Now, if I increase my power, transmitted power, the way that I was doing for narrowband, in here, the intersymbol interference also increases. So I cannot even remedy that. Even if I increase my power 1,000 times, the way that I was doing to make the fading go away, I cannot do that in here. So I better become smart. Otherwise, it's very destructive. So I'm looking for ways to go around with that. The ways that I can do in this is somehow I have to control this multipath. And this multipath, if I go in frequency domain, is what? If I get the Fourier transform in frequency domain, it is something like that. You remember that? Huh? And these things, this time is in frequency, not in time. These were called what? Frequency selective fading. So in reality, what is happening is that if I am in the narrowband signal, I'm operating either in here or either in here. Okay? So if I'm in deep fade, that's fine. The entire signal goes to the fade. If I'm in wideband communication, I'm something like that. Part of the signal is hit by good channel, part is hit by bad channel, or by fade, by frequency selective fading. If I'm not as smart, always I have a fade inside. Because if I get a wider bandwidth, probability of having a fade inside there is more. But if I'm smart, I can somehow take advantage of these good parts and eliminate the effect of bad parts. This is the art of designing broadband modems. Did you follow me? So, in narrowband communication, if I look at the frequency domain, I'm disturbed by frequency selective fading. Okay? And as time passes by, either I go to fade or I don't. Either entire signal goes to fade or entire signal is out of fade. If I increase my data rate, my bandwidth becomes wider, so the probability of having a fade inside the bandwidth increases. And I'm in deep trouble. Okay? In time domain, what happens? In time domain, what happens is this thing that I showed you. I will have intersymbol interference. So you can look at that from time domain. You can look at that from the frequency domain. Okay? In time domain, multipath causes intersymbol interference. In frequency domain, multipath if I increase my data rate, increases the possibility of having it fade inside my bandwidth, because I'm selecting a wider band. Okay? So this is the intuition that we want to develop. Remember, I want to only develop intuition. Okay? So with that story, if you want to summarize that story, let me see if I can. So I learned this one from Jim last week. I cleared the thing with one touch. Now, okay. So in summary, what I said in here is that for narrowband communication, pulse doesn't shape of the pulse doesn't change, but magnitude changes a lot. In wideband, shape of the pulse changes. Fluctuation of the magnitude becomes less, actually. Okay. And with that, I want to go to the next step. So if I have like narrowband communication and I want to send a pulse, the simplest pulse ever is a square pulse. If I send this square pulse at the receiver, I receive that square pulse plus this noise. This is additive noise. And then the total amplitude in here always goes ups and down due to the effect of fading. So it goes up, it comes down. But we don't use square pulses because in frequency domain, square pulses, the frequency domain, if you get the spectrum, these side lobes are like 13 dB below the top. So if I'm in the radio channel and I have one channel in here and I want to have another channel in here, I have a signal to noise ratio of like 10 dB already. So it's not good. So I try, as we saw in lecture 1, I try always to get pulses that they have these side lobes which are much lower. You remember that from like lecture 7. Okay. One of the most popular pulses that people use are the so-called sync pulses. And if you want to create a sync pulse, which is this particular sync pulses are called raised cosine pulses. Raised cosine pulses. Why raised cosine? Because a spectrum of these guys is like a cosine. Cosine is like this. Okay? Half of the I mean, this is the full. But if you take this thing, this is a cosine. Okay? If I raise this cosine up and cut this part away, I have something like this. This pulse is called raised cosine pulse. This is the spectrum of the pulse. And then sometimes they cut it in the middle and they put some straight part in between, one half cosine in here, half cosine in there. Still it's called raised cosine. And these are the pulses that you see in here in a spectrum. What is good about these pulses, it can be shown that in time domain, always they have zero crossings at t, 2t, 3t, 4t, 5t, etc. So if I send this pulse at the receiver, if I sample, if I have good sampling time in here, then the next pulse which comes, I sample it in here. So these side lobes are, effect of the side lobes are zero. Okay, that's the advantage of raised cosine pulses. Okay, then the next question is that this is the spectrum of the raised cosine. I want to create this raised cosine with a match filter. Means that I have one filter at the transmitter, one filter at the receiver. Both of them together should have this impulse response. What is the impulse response of each of them? This is that impulse response associated to each of them. These things you can sketch them and do. I have some homeworks at the end of the second book and this book as well, which you can sketch and play with that. But I don't want to go inside that more than what I told you about raised cosine pulses. And I want to just tell you what will happen. This is the figure that I showed you a little bit earlier. I mean, I tried to sketch it. If I have no multipath, first of all, generally for communication, I do raised cosine pulses in the modems. for the reason that I told you before, to control the side lobes. Okay. If I do raise cosine pulses, I send the first, second, third symbols, and then I sample them in here, here, here. And when I sample symbol 3, effect of symbol 2 and 1 are 0. When I sample for symbol 2, effect of 3 and 1 are 0. When I sample for 1, effect of 2 and 3 are 0. So that's why I select raised cosine pulses. Okay? So, but if I do my sampling a little bit back and forth with a little error, then I will have some effect of the others. So raised cosine pulses are much more sensitive to sampling time than square pulses. But what is the advantage of raised cosine pulse? Advantage of raised cosine pulse is that it has much lower side lobes. And I can control that side lobe by the parameter alpha, means that how straight it is in here. That is this parameter beta in here, in the equations, which governs this thing. Okay? Now, so if I have narrowband communications, I send a pulse, I receive the same pulse, raised cosine pulses, no problem, similar to voice band modems, and they are very good. I can use them. Okay? But how about if I have wideband communication? In wideband communication, I know that now if I have two paths, the two paths are apart on the order of symbols. So I send a signal, I receive one path in here and one path in here, and the overall received pulse is something like this. And this overall received pulse may not be necessarily 0 anymore at this sampling time. Okay? Since it is not 0 necessarily at the sampling times, what will happen is that I will have intersymbol interference. For example, I have this much intersymbol, this much intersymbol interference. Do you follow me? So, the raised cosine pulses are designed so that they are 0 at t, 2t, 3t, etc. If I increase my data rate, now the paths are coming away from one another. They are no more 0 at t, 2t, 3t, etc. So what will happen? If I look at the impulse response, for example, sampled impulse response for narrowband communication, it's something like that. 1, 0, 0, 0. If I want to think digital. So I send the first symbol, this is the first symbol. And effect in the others are 0. Okay? And if I go to wideband communication, the impulse response is in here something, and then I have some sides in there. So when I send my next symbol at here, the next symbol would be like this. And this guy interfere with this guy interfere with this. So the symbols interfere with one another. Okay? So this is the same phenomenon that I used to call it for intersymbol interference. Now, I increase the power, both signal and the side lobes increase, and I cannot solve the problem. Okay? So, it's not a bad idea to think in discrete manner. I like you actually to think in discrete manner. I'm talking about a fading channel. If I have narrowband signal, my impulse response is only one. Okay? One pulse, which is changing its amplitude according to the fading. It goes up and down. Now, if I'm somehow smart to measure the impulse response with the multipath fading, in multipath environment, I have several paths. I have an impulse response like this, for example. If I'm smart and avoid this intersymbol interference, if I look at each of these paths, each of them are like a source of diversity, actually, because they are going to fading independent from one another. Well, not necessarily correlated, but could be even independent. Okay? So, if I'm smart in wideband communication, I can take advantage of diversity of the signal. Because in wideband communication, my discrete impulse response is more than what? More than one tap. So each of these taps looks like an antenna. They fade differently from one another. So I have a source of diversity. So in wideband communication, I have in-band diversity. This is what I call it in-band diversity. Means within the bandwidth, still I have a raised cosine with the same bandwidth. But inside that bandwidth, I have more than one diversity. I have diversified signal. Where is that diversity? Inside my impulse response. If I'm intelligent, I take advantage of that. Or I create a situation that I can take advantage of it. If I'm not, those cause intersymbol interference. So the art of designing wideband modem is to avoid destructive effects of multipath spread and try to take advantage of the in-band diversity. So that's the art. And people have different techniques, like discrete match filter, equalization, OFDM, etc. They are trying to play some tricks to take advantage of this in-band. So this is the intuition that you want to develop here. Okay? We can't develop more than intuition in here. But before we go there, up to now, I just told you that that how multipath causes problem by changing the shape of the pulse. But I want to give you an example in here. And this example is effect of multipath on bit error rate. Because up to now, I was just telling you that multipath changes the shape of the pulse. But who cares about shape of the pulse? We care about bit error rate. So let's just get a quantitative now. If I want to calculate it now, it is a little bit like complicated. So I take like two paths, a channel with two paths. Path 1 has magnitude A1, path 2 has magnitude A2. The distance between the two paths is T, and my pulse duration is T. And I have raised cosine pulses. So my data rate is what? 1 over T. Okay? Now, the ratio of this T, which is what? T is my maximum multipath spread. Okay? Over capital T is the normalized spread of the pulse. Do you follow that? And then what I do is that I take like basic binary PSK modulation, for example, and I generate my pulses, and I calculate the error rate. How do I calculate the error rate? What I do, simply, I take these two paths, and I send one pulse, I receive another pulse, I create the overall impulse response, I sample them at T, and I will find this equivalent discrete impulse response. And then, whenever this guy, for example, is binary PSK, whenever this guy is 1, I may have this guy to be like 1 or minus 1. This one either 1 or minus 1. So they may add to that or they may subtract to that. They may add my signal to noise ratio. Do you remember that D over square root of N0 ERF complement? This D, if I have one channel, is this thing. If I have like intersymbol interference, it could be this thing plus this. It could be this thing minus this. Because intersymbol interference may add to the signal, may subtract it. So based on that, I can calculate from ERF complement function the probability of error. And this is that probability of error in here. For different possibilities of neighboring bits. The neighboring bits could be the same as mine or could be different from mine. And if you calculate that probability of error versus T over capital T means that multipath spread over duration of the pulse or transmission period. I get something like that. At the beginning in here, when it's 0, means that the two paths are on top of one another. My error rate is 10 to the minus 8. Okay? As I'm increasing in here, I'm having the second path. This is the first path. Second path is moving away from this path, causing more multipath spread. And the error rate starts to deteriorate, depending on the ratio of these two. This is A2, this one. A1, I assume it is equal to 1. So I keep the first one 1. The second one is first 0.1. Then it gets increased to, I believe in here is something like 0.5 something, and in here is something like 1. Okay? So I'm increasing the second path, the amplitude, and I'm changing. As the second path amplitude improves, my data rates, my error rates drops. So I see that, for example, for this bad condition, I go from 10 to the minus 8 to 10 to the minus 1, which is a very bad error rate, unacceptable. 10 to the minus 8 is acceptable for voice and data. 10 minus 2, less than 10 to the minus 2, is not acceptable for anything. Okay, so this is the basic thing which happens. As I'm changing A2, I'm changing really tau RMS. As tau RMS is increased, the effect of multipath is going to increase. Okay, if I go from here, compare here, here, here. And also, I'm increasing the multipath in this direction too. As multipath spread is increasing, by changing the tau, also my error rate decreases. So there are two sources which are causing errors in multipath. One is the spread of the channel. The other one is the strength of the second path. Okay. Usually we combine both of them in one parameter, which is tau RMS. And you can get similar results for that as well. Then you don't need to have 3 paths, for example. 3 different type of A. Anyways, so basically from this figure, what I do is that, the conclusion that I get is that as I increase the multipath spread, or I increase the power of the multipath components, performance will degrade. And it will degrade significantly. If you remember, if I want to go from 10 to the minus 8 to, for example, 10 to the minus 5, in non-fading channels, like I have like about 3 dB for each of them. And I have to compensate. In fading channel, it's a lot more. It's like 10 dB for any of these tickers. Okay, so I have a lot of damaging effect because of the multipath. Okay, so that was the main essence of this thing. I call this type of situation when R, which is 1 over T, is comparable with 1 over tau RMS. We call this like this multipath. If I have data rate like that, I call it wideband communication. And the channel which exists in between, I call it frequency selective. Frequency selective channel. Why I call it now channel was always frequency selective. Why do I call it frequency selective now and I was not calling it before? Because I told you, when I make my bandwidth wider, part of the band goes to fading. And part of the band is not in the fading. Means that the bandwidth of my signal is comparable with the width of these things in frequency selective fading. In narrowband communication, I'm like this, very small band. You follow that? So either my channel hits the frequency selective fading or it doesn't. In wideband communication, part of my channel is get hit with the deep nulls or fading, frequency selective fading. Okay, so this type of situation happens when I have this RMS multipath spread going with this condition. As a result, sometimes when you read the literature, they say communication over frequency selective fading channels means that broadband communication, wideband communication. Sometimes they call it the channel is flat fading, means that I'm talking about narrowband communication. And sometimes it's very confusing because I look at the channel, it's always wideband. Okay? Always it is frequency selective. But no. Means for that particular modem, I have this condition or I don't have this condition. So I can call it narrowband and wideband equivalently. Narrowband communication in information theory means communication over flat fading channel. Wideband communication in information theory is translated to communication over frequency selective fading channels. Okay? These are just different terminologies. Okay? Now we go for some examples, some experimental results. These are some numbers that one of my students, Steve Howard, did as a part of his PhD thesis long time ago, like 1991, around 1990. It was published 1991. What he did, if you remember earlier, I talked about some indoor measurements that another student of mine, Ganesh, did, and he collected a bunch of channel impulse responses in different offices and manufacturing floors. These are 5 of them. 5 set of channel impulse responses. Okay? One of them is in office, the other one in manufacturing floor. 2 of them in offices, 2 of them in manufacturing floor. Descriptions are in the textbook. But there are 5 different areas. And in each area, I have a bunch of impulse responses, which I really have measured from the channel. So what Steve does, he gets Ganesh's, in fact, channel impulse responses, and for each of them, he calculates an error rate similar to error rates that I was calculating in here. This is real, based on data rate. But what he does, he changes the data rate. It's 100 kilobit, 1 megabit per second, up to 16 megabit per second. And what he does, he calculates probability of outage. Okay? Outage from threshold of 10 to the minus 2, threshold of 10 to the minus 4, threshold of 10 to the minus 8. Do you remember? When we define probability of outage, we have to say outage from what? I have a threshold error rate. That threshold error rate could be 10 to the minus 2, 10 to the minus 4, 10 to the minus 8. So I have a bunch of 100 channel impulse responses, for example. I calculate error rate for all of them. And then what I do is that I will see in how many places I'm less than 10 to the minus 2, for how many places I'm worse than 10 to the minus 4, for how many places I'm worse than 10 to the minus 8. That's how he calculates these numbers. And he creates this table for different areas. Now, looking at that, let's look at the first one, for example. In first one, I see that in indoor areas, I have error rates of 0.1, 1, 2, 3, etc. If I take the middle one, 10 to the minus 4, for my threshold, I see that in like 1 megabit per second, I have like probability of error of 2 times 10 to the minus 3. Good for voice communication. If I come to 16, my probability of outage is like 1%, 10 to the minus 1. Means that 10% of the locations I have bad result. In here, I have like 2 or 3 actually, this is 2.9, 3.3%, 0.3 over 1 means that in every 1,000 location, 3 locations, my error rate is less than 10 to the minus 4. So if I'm looking for like a good data rate in here, I see some, depends on what is my threshold and what I will accept. If I look at all of these things, I will end up that like if I accept outage rate of 1%, for example, 1%, 1%, and then 1%, this is close to 1%, this is close to 1%, this is close to, as close as I can get between these two. I look at all of these guys, I see that the data rates between 1 to 4 megabit per second provides an outage rate of like 1%, around 1%. 1% outage rate is acceptable because 99% of the locations I have good signal. 1% I don't have good coverage. And in that 1% I can move my laptop a little bit, possibly. But it depends on what you want to say. If I go with that 1%, I see there is a relationship. Data rates around 1 to 4 megabit per second are the data rates which are acceptable for what? For indoor channels. What was the TRMS for indoor channels? Do you remember? TRMS for indoor channels, TRMS from the same measurements, if you remember, was something roughly around 100 nanosecond. What is the inverse of 100 nanosecond? 1 over 100 nanosecond is 10 megabit per second. So if my data rate is like 10% of that, I have good data communication. Do you follow? Up to now, I was telling you my data rate should be like something less than 10% of tau RMS. And in here, I just showed you that. Okay? That this is how it works, and this is how we can relate these things. The relationship is not exact one-to-one, but they are just some engineering guides. Okay? And the meaning is what you see in this particular, in fact, example. So this was my example. Again, example 2, if you want to call it. The one before was example 1. So up to here, what I did, basically, I told you that if I increase my data rate, for example, in an indoor area, like in example 2, when I go above 1 megabit per second or something, I expect that my error rate is going now to be increased to the extent that is not useful. Or if I'm looking at probability of outage, my outage rate becomes unuseful. Okay? So I want to find those limits and work on that. And I know the source of this thing is something like this thing. The source of problem was what? The source of problem was this, multipath. This is what? This is the channel impulse response. Discrete channel impulse response. This is discrete channel impulse response. Discrete channel impulse response. Okay? So now I want, and in here, my discrete channel impulse response in here was, for each point was different. It was something like this, similar to the measurements that I had done earlier and I have shown you earlier. Okay? Now, the question comes that how can I, the impulse responses that I had in here was really something like this. Okay, that was the impulse response. And the pulse which was transmitted was something like that. How can I combine these two and come up with one single overall channel impulse response? To be more specific on that, let me come in here. This is the famous figure 1 for all the communication systems. I have a pulse shaping filter. This is a baseband transmission. I have a bunch of impulses coming inside, and these pulses are my transmitted pulses. Assume I have like binary PSK, a simple thing. If it is binary PSK, A sub n is plus minus 1. Okay? So I have these pulses which have positive and negative polarity, and the shape of these pulses are f of t. They pass through a channel. This channel has impulse response like this, h of tau and t, if you remember. Channel impulse response is a function of time and what? Delay of arrival of different paths. So if this is my transmitted pulses, the received pulses would be this thing plus additive noise. What I receive in here would be this thing plus this additive noise. What is this G? G is really convolution of this F and this H, which is given by this equation. Okay? And then I pass it through an ideal low-pass filter in this particular case, just to make my life easier. And then my received signal, after that, I will sample it. If I pass it through an ideal low-pass filter, nothing happens. The same R sub t comes in here. Just the noise is going to be bounded. But what will happen is that at this place, I'm going to sample this signal, and I sample it at n over 2 f naught. F naught is like a frequency that I can say is my transmission frequency. 2 f naught is my Nyquist rate. So 2 samples per pulse, so that I can reproduce the signal. The bandwidth of the signal is f naught. I sample it twice the bandwidth. The samples that I have contain all the information about the bandwidth. So I sample it at 2 f naught. So this is my received signal. I sample it at 2 f naught. I sample the noise and the received signal based on that. Then I will have like sampled output signal, which is something like this. It's sampled noise and samples of this signal, which I can represent them by this. The input in here was a sub k. In here, I will call it x of k. X of k really is a sub k with a little bit different touch. Because my data, a sub k, is coming like this. I have 1, and then t after that, I have another bit. But this sampled signal is at Nyquist rate. Do you follow what I say? The sampling rate that I have in here is not at 1 over t. It's at 1 over 2 f naught, which if you want to, the sampling is not at t. It is at 1 over 2 f naught, which is really 1/2 of t, t half, if you want to call it. Okay, so I'm sampling the signal for equivalent channel impulse response at a data rate, at a rate which is twice the transmission rate. So I'm sending these bits, I send this thing, and then t times after that, I send another one. But when I'm at the receiver, I take a sample in here. For this sample, what was the value of the transmitted bit? Was 0. Okay? So this x of n is a over n over m when and 0 other places. Means that I have these transmitted bits. I can take as many samples in between, not necessarily not necessarily relating f naught with t. I can have m samples per 1 transmitted pulse at the receiver, and these m samples, in terms of data, this is A0, this is A1. In between, I have zeros. These are those zeros. These are non-zero values. In another sense, in another word, what I have told you in here, I can take this f naught anything, actually. And I say that at the receiver, I'm sampling. I'm sampling at the receiver at a rate which is m times faster than transmitted bits. So every bit that I send in here, 1 bit I send, and 1 bit I send. These are the transmitted bits. Associated to each of these, I will receive some pulses like this at the receiver. These pulses are not sampled only one in here, one in here. I have sampled them like many in between to come. I take m samples per each of these things. Okay? If I do that type of thing, then my equivalent channel impulse response would be something like this. The data which is transmitted is something like this and this, for example. This is one model that I can develop for overall channel impulse response. Okay? So if I want to show it in discrete form, this is in discrete form. These are the transmitted symbols. These are this thing, and then 0, 0, 0, 0, 0, m of them, and then this. This is A0, A1, and etc. It passes through a tap delay line. Each of these taps have a gain which is defined by this equation. And if I want to normalize, I get all of these tap gains, magnitude square, and I put it equal to 1. Average of that, or expectation of that. Okay? And then the output, I have some noise added to the output, plus R sub n. I mean, the output is R sub n. This is a discrete equivalent of what? Of the entire system that I had in here. What was the entire system? A transmitter, channel, additive noise, receiver filter, and sampling after that. From here to here, I model everything with this tap delay line, which is nothing but what? An FIR filter. So I have X sub n as the input. I have an FIR filter. And then I have this noise, sampled noise, 8 sub n. And then my output is like this, R sub n. Bottom line is that if you go to the, and this is very good for any type of signal processing, because when I implement the modems, I do sample the same way. I do sample them faster than the T, and I process them like that. Like in voice band modems, for example, the baud rate is 2400, they sample it at 9600. Okay? But they don't have multipath. In here I have multipath. Okay. So I have a channel model. So the general channel model, the general thing that I have is that I'm modeling the channel with an FIR filter running with X sub n. X sub n is like the data and padded with zeros in between, and then the next data. Output is my receive signal. This FIR filter is overall discrete channel model. This is the thing which represents the channel. This is an FIR filter which has taps equally spaced, okay, and each tap is a random variable. These random variables are changing in time according to the fading characteristics of the channel. Okay, I can generate that for anything. But if I generate it like that, now I can develop intuition about what is going on. So basically what I have told you so far was that if I want to model the channel is modeled by what? By a tap delay line. Tap delay line is the old name for FIR filters. An FIR filter with what? With impulse response like this, for example, in which each of these are changing according to fading. Have you seen something similar to that? Yes, we saw all the models that we are using earlier in the previous chapters, recommended by GSM or whatever. All of them, they were a bunch of tap delay lines. But the distance between the taps were not necessarily related to the bandwidth of the channel. Okay, the way that we have related it in here. So basically what we are saying is that if you want to simplify everything for any sort of transmission technique, you can take the entire thing and assume that I have a channel model in between, and data comes in, data goes out. I mean, the received signal goes out. If I have this type of model, then I can have like easier time to like express different or find different methods to handle the situation. So reality of the matter in a fading channel is that my communication is like this. I'm sending these bits, I mean in discrete form. I'm sending these things. These are different bits. Okay? And they are passing through a channel. The channel impulse response is something like this. The length of this thing could be less than this, could be even more than that. If this length of the channel impulse response, this is my, what I called it, if you want to call G or F, I called it G of N. Okay, G of N, I call it something like that. Okay, these are those tap delay lines, values of those tap delay lines. The length of these tap delays could be more than that, could be less than this. If it is less than this, I don't have intersymbol interference, is narrowband communication. If it is more than this, I have intersymbol interference, I have wideband communication. So in this case that I have in here, since the duration of the pulse in discrete form is more than distance between the two symbols, I have intersymbol interference. But anyway, my channel is this thing in discrete form. And I don't need to worry about any modulation, demodulation, or anything like that. With that, I cannot develop some understanding, better understanding. So channel model is a bunch of taps, and these taps are not fixed, they are changing. So the first question is that if I want to have a smart receiver, what should I do? A smart receiver is the one that can measure these values. Because if I cannot measure the sampled impulse response, what can I do? Either I have to measure them or find somehow, some way to counteract their effect. So I have an impulse response. The first easiest way is that I measure that impulse response. How can I measure it? Measurement of these things is not that difficult. The easiest way is that these are what? These are fading channels. They're going up and down. This is something which goes up and down like this in time. If I pass that through a filter, just through a low-pass filter, what will happen? If I pass through a low-pass filter, it takes the average of all of this. That's one thing. Okay, I can take the average of that if I want to find the average of that. Okay, I can also trace these things. If I put this thing, for example, the bandwidth of this thing, if I want to take just the value of these things at each location, if I don't want the average, I want just the average, I just read them. I read the value of these tabs with one sample. I have the value at that time. Okay, so I can play with them. I can measure it whichever way that I want. Now, there are two ways that you can do that. One is that you can get these received signals, and I mean, I have not the proof in here, but there are references for the proof. I can take the received signal. This is what? Rn is the output of that FIR filter. FIR. Okay, this is what I receive, the sample of the signal that I receive. And then, if I know that what was transmitted, I pass the transmitted signal through a tap delay line, and then the received signal samples I multiply it like this, in this structure. And then I pass them through low-pass filters. I have estimates of those taps. These are estimates of channel impulse response. This is the first path, second, and this, etc. This is one way to estimate the channel. Okay. So this is actually maximum likelihood estimation of the channel. As I said, detail of that are available. Actually, I did some of those in 1979. One of my early papers is about this thing. But I don't want to go to detail of that. But basically what you're doing in here, you're assuming that transmitted signal is known. But, I mean, in real world, I don't know what is the transmitted signal. So how do you do that? I send some training sequence. For example, like if you have GSM signal, what do? For the GSM, inside the packet, they have like certain training bits. Like they have like 26 bits per packet, which are known bits. And I use those bits to estimate the channel. So I put those in here and receive signal associated to that in here. In this structure, I measure the impulse response. Okay, that's one way to measure the impulse response. The other way is, this is maximum likelihood, minimum mean square error. Minimum square is a structure like this. This one also is available in variety of sources, including my thesis, like very old one, and also John Prokis's book. Basically, for those of you who have seen equalizers, if you use least mean square criteria to estimate the location of the taps or value of the taps, you can calculate them out of this equation. This delta is a fixed parameter that you can select. This error in here is the difference between these two, the received signal and the estimate of the received signal. So basically, the received signal is coming in, and then delta is this number in here. The data x of n, the known data or training sequence, comes in here, passes through this. This is really truly another FIR filter whose taps are adjusted by these values. So if you want to say the impulse response of this guy is like this, G0, G1, etc. This is the impulse response of this filter. How do you calculate G0, G1, Gn? According to this equation. Okay, but when the signal comes inside of this filter, this FIR filter, the output x of n comes through this FIR filter. The output is your R sub n. Hat, actually, I call it. Okay, that's estimate of R sub n. That estimate, you compare it with the actual sampled signal, sampled received signal. So received signal was coming through another FIR filter, which was the channel, G, whatever I call it. And the output was R sub n. This is what I have received at the receiver. Now, at the receiver also I have another FIR filter, which is G hat, which is the estimate of this filter. Okay, output of that is Rn hat. This is what I create at the receiver. Difference between these two is my error function. In here, this error function is here, error. Or I multiply it with this, and then I adjust the taps. So with this simple algorithm, this is my error, received signal, minus estimated received signal. I put it inside here, and these taps adjust themselves. Delta is a very small parameter. If you want the detail of implementation of this, proof for that, the best reference could be John Prokis's book. If you want older material related, that my thesis, 1979, has like this stuff. But the point that I have in here, up to here, what I'm telling you is that you have simple structures which are available in the literature with which you can estimate the channel impulse response. And what is the meaning of channel impulse response in here is a little bit different from what we had earlier. This is channel impulse response inside the modem, not the channel itself. Okay? So it is a function of bandwidth of the transmitted signal. Okay? So if I have a transmitted signal, at the receiver, I'm sampling that at a rate something like 4 times the bandwidth, for example. Okay? So I have 4 per transmitted pulse. And I can measure that impulse response. And if I measure it, in summary, my system is represented by a filter called G, for example. The received signal X of n is transmitted, received signal is R sub n. This G is something like this. Then at the receiver, I take this sample signal. Actually, this R sub n, I have also some noise in there at the sub n. Okay. At the receiver, I take this R sub n. I pass it through a channel estimator. Channel estimator really estimates this thing. Estimates this impulse response. Okay? And then, now I want to see what to do with it, with this channel impulse response. Okay? This is what I have told you. This is the receiver. This is the transmitter. I mean, transmitter plus front end of the receiver. So if I want to think about it, up to here, this is what I have told you. Okay? Now, these things that I can measure them instantaneously are the value of the impulse response of the channel, which in a way they are my in-band diversity sources. Okay? So I'm looking at this system from signal processing point of view. I'm sending a bunch of bits, and at the receiver, I'm receiving impulse responses associated to them. Okay? I have an FIR filter, I'm running that. And I can estimate that impulse response. Now, what can you do? And that impulse response, each tap of the impulse response is like an antenna, because they are fading differently from one another, but they are related to the same bit. Okay? So now what can I do to improve this thing? I mean, so if you remember, up to now what I said is that channel is represented by a bunch of, if I have like broadband or wideband communication, the channel is represented by an impulse response. And each taps of this impulse response is like a fading value, which is going up and down. Okay? Now, how many tricks I can play to improve it? The tricks can be divided in, I can use coding, I can use discrete match filtering or rake receiver, I can use maximum likelihood sequence estimation and discrete Fourier transform. Decision feedback equalizer. These are the 3 techniques that I will call them time diversity techniques. And I will discuss that in the second part of the lecture. Then I can use OFDM, which is using the so-called frequency diversity. And then I can use multiple antennas or smart antennas, which I can call them space diversity. Or I can combine them. Like I can combine the space-time diversity and MIMO. And with each of these things, I'm somehow taking advantage. To start with, to explain that how I'm taking advantage, I go to this 2, because coding was covered in the previous one. So I talked about discrete match filter and rake receiver and decision feedback equalizer and maximum likelihood sequence estimation. These are the second part of the lecture. But right now we take a break, and when we come back, we talk about that. So in summary, what I told you in the first part of this lecture, I told you number 1, if you have multipath, you are in deep trouble because you have inter-symbol interference. If you are smart, you take this multipath and you try to use it actually, because these are multipath as different antennas. just like different antennas, and provide diversity. Okay? Then, if you're not smart, it goes to intersymbol. That was one thing that I told you. The second thing that I told you was that now I want to introduce you the techniques. If you want to look at those techniques and have some intuition, it's better to look at this discrete model, which anyhow, in digital implementation of any modem, it exists. And basically what I told you very roughly and with very sketchy math, I told you that you can take the channel after, you send the pulses, you receive it at the receiver, you pass it through an A to D converter, and you sample it. Okay? Now, those samples that you're receiving really are output and FIR filter. And taps of that FIR filter are fading taps. They are not fixed, they are changing. This is what I told you for the channel model. And now, having that channel model in my back of my mind, when we come back, I tell you how we can exploit it to do like discrete match filtering and equalization, which I refer to them as time diversity.